Hello class, we're about to start section 2.5 on page 165. Our lesson is sit back and watch your money grow. Learning objectives. 1 is to illustrate exponential growth with a graph. 2, to solve problems using graphs representing exponential growth and decay. 3, identify the significance of the parameters in an exponential equation. 4, find and interpret exponential models. Now we go down here to problem number 1. It says describe the differences between linear and exponential growth based on what we know from earlier in the course. Okay, first of all, we know linear growth is steady. You keep adding the same amount to get the next value. Exponential growth grows faster and faster by multiplying the same amount. To get the next value. Okay, number 2. It says, what do you think is meant by the relative change in a quantity? How do you compute relative change? Relative change, it is the size of the change expressed as a fraction or percentage of the original size. Okay, it also asks us, how do you compute relative change? So to calculate relative change, you divide the amount of the change by the original amount. And of course, we'll go over that as we proceed through this lesson. Okay, so now we move on to the next page. On the next page, it says if you're like a lot of people, you go on a spending spree if you won $10,000 on a game show. But what if you decided to invest that money rather than spend it? And what if you were patient enough to let it grow for 40 years in a savings account? Let's take a look. Make sure that you answer every question with a complete sentence. All right, it says for each value in the table after the initial investment, divide the amount by the value of the account the previous year. What do you notice? Okay, so we go here to our Desmos calculator, and we would take 10,700 and divide it by the previous year's amount, which is 10,000. We get 1.07. Okay, now we would take this 11,449 and divide it by the previous year, which is 10,700, and we get 1.07. Now I'm going to jump down here to the last one here. This will be 16,000 57.81 divided by the 15,007.30. Now, if you notice here, if we round to two decimal places, we have the same answer. And that will happen, especially when we're dealing with money. So we could say that each one of these are being multiplied by 1.07. So we could put every time we get 1.07 or something very close to it. Now it says number 4, what does your result in question 3 say about the type of growth this account exhibits? Okay, so I need to add on a little something here because every time we got 1.07 or something very close to it, so we would multiply each value by 1.07 to get the next value. Now, since we answered that in 3, now we can answer number 4. What does your result in question 3 say about the type of growth? We could put since we would multiply each value by 1.07 to get the next value, we are doing exponential growth. Okay, number 5, it says find the relative change in value for each year in the table compared to the previous year. What can you conclude? Okay, so this is what they want us to do, and we're doing the relative change here. So the relative change goes like this. We're going to still divide by, let's go back here on Desmos. We're still going to divide by the previous year, which would be 10,000. According to the table here, 10,000 is a 0 year. So we're dealing with this year here, the 10,700. So the first year, instead of taking 10,700 divided by 10,000, with relative change, we're going to take the 10,700 minus the 10,000 from the previous year. So that'll be 700 over 10,000. And when we put that in our calculator, 700 over 10,000 gives us 0.07. That is our actual relative change. Now, there's something else that we did before in the previous chapter that we used to get a value like this. When we did percent increase and percent decrease, remember how we took the new minus the original divided by the original? That's exactly what we're doing here. The new value would be this first year. The original value would be the 10,000, which is the 0 year, divided by the 10,000. And that's what they would want us to do for each one of these problems. So if we go here, the next value, the new value will be 11,449 minus the original value, which would be 10,700 divided by the 10,700. So it'd be 749 over 10,700, which would give us 0.07. Now, I'm not going to go through all of it, but I am going to go over the last two values to see if it keeps being at 0.07 or very close to it. So we would have 16,057.81 minus the 15,007.30 divided by the 15,007.30. Now, when we subtract this, this will give us 1,050.51 divided by the 15,007.30. Now, we'll put this in our calculator, which would be 1,050.51. And we will round that to the 2 decimal places, which will give us 0.07. So it actually works. And it says, what can you conclude? The relative change is 0.07. Or you could say the change, well, the relative change is 7%. Now, we move on to the next page. It says here, here's a quick summary of what we learned on page 166. The account starts at $10,000 and grows by 7% each year. Mathematically, this is accomplished by multiplying the previous year's amount by 1.07. So after 1 year, the amount is 10,000 times 1.07. After 2 years, it's 10,000 times 1.07 times 1.07, and so on. The result is that an equation that describes the value at the x years is y equals 10,000 times 1.07 to the x. And now we know why this type of growth is called exponential growth. We can use an exponent to represent the repeated multiplications that we get when a quantity is multiplied by the same amount over and over. So number 6, it says verify that the above equation generates the account values in the table. Ideally, you will use either the table feature on a graphing calculator or a spreadsheet. But in any case, make sure you describe how you got your values. Okay, so this is what we're going to do. We're going to type in this equation, which would be y equals, and then it'll be 10,000. And then we're going to do a parenthesis, 1.07, close the parenthesis, and then we're going to take this to the x power. So we will hit here, hit x. Okay, so we have our equation here. Now, they want us to prove that using this equation here, we would get this table here. So what we would do, we would hit this wheel, and we would hit the table. Now, what we need to do, we want to go from 0 to 7. So we'll go 3, 4, 5, 6, 7. So now we're going to compare. Now I'm going to have to expand this a little bit. Okay, yeah, that's good. All right, so we go here 0. 0 is 10,000. 1 is 10,700. 2 is 11,449. 3 is 12,250.43. 4 is 13,107.96. 5, we have to round to 2 decimal places, but it'd be 14,025.52. 6 would be 15,007.30. And then 7 would be 16,057. Now it has 815, so I'm imagining that it was some numbers behind that, but it's supposed to be 0.81, so it was just slightly off. But this actually works. So now, we are asked here to describe what we did. So to describe what we did, we put the equation in Desmos and created a table and entered the values. That's basically what we did. Oh, and one other thing. And in some cases, we had to round to 2 decimal places. So we have to include that. All right, now, number 7. It says, oh, and just to say this, I'm not going to do it all the way out, but those of you that are using the TI calculator, let me pull that up. I'm going to show you this really quick. With the TI calculator, you would type in the equation, you would press y equal, the equation was 10,000, parenthesis 1.07, close the parenthesis, and then you would take it to the x power. Then you will press second and graph to go to the table, and then you will go down. Now, here's the thing with the TI calculator. You have to go over to the Y value to make sure there's no values behind the decimal. Because you see it doesn't show that here. You have to go down so you can get all the values that's behind the decimal as well. Okay, and also here, when we got to 7, remember how I told you when we got that, let me go here. When we got this 5 here, when we get to 7, it was 16,057.8147. This only rounds to 3 decimal places. That's how we got the 0.815. So like I had said, it was supposed to still be 0.81. So this is how you basically do it in the TI calculator. Now, number 7, it says, look back at the graph that illustrates the value of the account. Trace along the graph slowly from left to right and describe what the change in steepness of the graph tells you about how the value is growing. Okay, basically, we don't actually need to necessarily do that in the calculator. We can look at this graph here. If you look at this graph here, you notice that it's steadily going up and it's going faster. So basically, you could say the graph does not start off very steep, but as you move to the right, the graph begins to grow faster. That's basically what it's telling you. Okay, now we'll go here to the back. It says number 8. How much interest will you earn from 0 to 5 years into the investment? This will be the difference in the value after 5 years in the initial investment. First, estimate the answer by looking at the graph, then perform a calculation using the table provided. Okay, let's do this on Desmos. Let's get this graph. So we'll press, we have our Y is equal to 10,000. And then we will have our parenthesis, 1.07, close the parenthesis, taken to the x power. Okay, now, if I go here to the graph, I have to go, you notice here I gotta basically zoom in order to get this graph. See if I could pull it down. Okay, so now, if you notice here, we actually went here on the negative side. That is very weird. Wait a minute, it seems as though something is, oh, you know what? I know what, I need to get rid of these. All right. It seems like it still should have. Hmm. That is very weird. Okay, class, I had to change the x value so that we could see the graph crossing the y-axis, because remember, originally the graph just looked like it didn't go across the y-axis, but I had to change the x values. And just to show you how you could change the x values, if you click this wrench here, you have the x-axis and you could change the values from the x-axis here. And so I changed them. You could type in whatever values you think would be good. And I changed them so we're able to see it now. All right, so now we look here at this graph, which we have, and they ask us here to find out what it is from 0 to 5 years. So what we could do, we could click here. We know at 0 is 10,000, and we would just go here to where X is 5. And if you look here, it looks as though it's about a little over 13,900. Trying to ease it here. Sometimes it's kind of hard. Yeah, okay. It's $14,025 and about 52 cents, according to this. And it's basically on your table as well. So it says, so basically, so we would take the $14,025.52 that we got, and we would subtract off the initial investment of 10,000. So our interest would be $4,025.52. So that is our interest, $4,025.52. So what we could state here is, oh, just give me 1 second. So we need to write this out in a statement. So let me shrink our Desmos calculator. All right, so we could say the interest earned from 0 to 5 years was $4,025.52. Okay, now number 9. It says, how much interest will you earn between years 35 and 40? Again, estimate from the graph first, then use the equation you wrote to get an exact value. So we can go back here to the graph. We can click here. So years 35 to 40. Just keep moving. All right, I'm going to have to take this out a little bit. So a little bit more. Let me do it like that. Okay, from year 35, so it'd be 106,765.82. So 106,765.82. Now that's year 35. 106,765.82. So then we will go to year 40. 149,744. What else? 149, 744, 58. Okay, so this is year 35, year 40, based upon the graph. So now we want to figure out the amount of interest that's earned, so we could do some subtraction. So we could take 149,744 and 58 cents minus 106,765.82. So your actual interest is $42,978.76. Okay, now there's another way we could do this as well. If we went back here, and I had took the table off, so let me put the table back on here. If we go back and put the table back on here, there was actually an easier way for us to get the 35 and 40. We could have went to the wheel, created our table, and we could have typed in the years that we wanted. We could have typed in year 35 and then also year 40, and would have given us the amounts that we needed. As you can see here, this right here, of course, we would have to expand it out, but it will round up. This should be to 82, but yeah, we could have put that in for 35 and 40 years. That's another way of doing it on Desmos. Now, number 10, it says describe what you can learn from comparing the answers to question 8 and 9. Also describe how that fits in with your answer to question 7. The first 5 years interest was $4,025.52, and the 5 years from years 35 to 40 was $42,978.76, which is over 10 times the amount of interest. So interest grew faster as time went on, which is basically what we stated before. The longer the time, the more interest was made. Okay, now, basically question number 11 was basically like an extra question that I'll do 11, but we're not going to do 12. It says here, my all-time favorite TV show was Highlander. It featured a race of immortals whose destiny is to battle each other over hundreds and in some cases thousands of years. The fact that most of them appear to be fabulously wealthy strikes a lot of people as hokey, but based on what we've learned in this lesson, it actually makes a great deal of sense. Suppose that you could travel back in time to the year 1700 and invest a very modest sum of $10. Suppose further that the investment draws a very modest return of just 5% each year. Comparing to the equation at the top of page 167, write an equation that would describe the value of the the account after X years. So basically it goes like this. The formula we use is y equals AB to the X power. Okay, now A is the initial amount. B is the growth rate. And X is the time. All right, so we just need to substitute. A is the initial amount. We said it was $10. B is the growth rate. Now, they say that it's growing at 5%. Growth rate is 1 plus whatever the percent is. So the percent is 5%. So 1 plus 5% would be 105%. And then to the X power. Now, when we write in this parenthesis like we did in the previous problems, this has to be changed to a decimal. So it'll be y equals 10 times 1.05 to the X power. And this is the actual equation. All right. So now, they also asked us write an equation that would describe the value. Okay, so we actually went through all of that. Now, I guess I might as well go ahead and do problem number 12. It says use your equation to find the value of that $10. That $10 investment. Now, remember your variable X represent years after 1700. So basically, we will have this formula, which we wrote on the previous page. And then we want years after 1700. Now, we're in 2020. So what's that? 320 years. So we have y is equal to 10 times 1.05 to the 320th power. Now, we could do this here. I'm going to alter this equation. So this will be 10 to the 1.05 power. And I would change this to a table. And then I would just type in 320. And you see this is a very, very large number because we ended up having scientific notation here. So since this is times 10 to the 7th power, that means I'm going to write this out. 0.33589 times 10 to the 7th power. Now to write this out as a regular number, we will have to move this decimal 7 places to the right. So it'd be 6033589. So this person would have $60,335,890. That's how much they would have after investing the $10. All right. So now we move on. We actually have a few more pages to do here, starting with the bottom. Now we have this table here. Now what I want to do before we move on and make this a little easier, I'm going to create this table in Desmos. Let me just create this table so we will have this ready and available. So it'll be 0, 1, 2, 3, 4, 5, 6, and 7. Then we will type in these values. We got 180, 144, 115.2, 92.2, 73.7, 59, 47.2, and 37.7. All right, so we created this table. Now it says here, we've now studied exponential growth a couple of different times in this unit, but there's a flip side to exponential growth known as exponential decay. So this would be considered exponential decay. The thing that distinguishes exponential growth is that the growth starts off relatively slowly, then speeds up dramatically as time passes. Let's see how exponential decay compares. Coffee is a popular morning drink because the caffeine it contains acts as a temporary stimulant. Once the caffeine gets into your system, the amount dissipates exponentially, assuming that you don't add more or of course. Answer every question except for 2 and 6 with the full sentence. All right, so we go here to the back. It says number 1. If you're the coffee drinker represented by the table and graph, how much coffee was initially in your system? Now, initially in your system is that 0 point. At the 0 point, we have 180.0 milligrams of caffeine. That's how much was in your system. 100.0 milligrams of caffeine, because they want us to write this as a sentence, was initially in your system. Okay, now we move on to number 2. It says find the relative change in caffeine for each 1 hour period listed in the table below. Round to the nearest 4%. Okay, so if we look here, going back to the table, so we would take the 144 and we'll put a division here, minus 180 divided by the 180. Because remember, we'll take the new value, which would be the 144, minus the original divided by the original. So that would be a negative 0.2. So we'll write that as a percent. Negative 0.2 is the same thing as a negative 20%. So what I'm going to do, I'm going to do the last one because I don't want to do each individual value. We could just go right to the last one. And we will have basically 37.7. 37.7 minus 47.2 divided by 47.2. And it gives us basically the same thing. So it still will be a negative 20%. So we're going to assume that all of these will be a negative 20%. So that will be the relative change. Okay, number 3. It says, complete this important statement about exponential change. A quantity either grows or decays exponentially when the relative change in the quantity is equal. And number 4, looking at the graph of the caffeine remaining in your system, describe what exponential decay looks like compared to exponential growth. They look opposites. They look like opposites. Exponential growth from left to right curves upward. Exponential decay from left to right curves downward. Okay, number 5. It says, what's the multiplication factor that you need to multiply by a previous hour's amount to get the next hour's amount? Hint, if 10% of something goes away each hour, 90% remains. Now let me explain this. You start out with 100%. Now, when you start out with 100%, if you're going up, it'll be 100 plus whatever that percent. But with decay, we're going down. So they're saying here, if you go down 10%, that leaves you 90%. So we're going down 20%. So our answer here would be 80% or 0.80. Okay. So now we move on and we go to problem number 6. It says use your answer to question 5 to write an equation of the form y equals expression, where the expression describes the amount of caffeine left in your system after X hours. Your answer to question 11 in the class portion. Okay, basically they want us to write out the equation y equals AB to the X. Okay, we know our initial amount was 180.0. You could just write 180 because it means the same. Now our B, when we subtracted that 20%, that left us 0.80. That's our decay factor, and it's to the X power. Okay, number 7. It says use a graphing calculator to verify that the equation you wrote in question 6 gives you the values in the table in the given graph. Okay, so now we're going to write out the equation because I put the graph here. So we have y is equal to 180 parenthesis 0.80, and then we want to do that to the X power. Okay, then we go here to this wheel and we go to the table. Now I want to take out the -2 and the -1. If you take that out, basically the same exact thing. You have 0, 180, 1, 140, 115.2. We have to do 3, and it gives us the 92. We round it to 1 decimal place. Then 4 will give you the same thing, rounded to 1 decimal place. 5, 6, and even 7. All rounded to 1 decimal place, it will give you the same values. So it does work. And then it says describe your results. Results are the same as the table. Now it says use the trace feature on your graphing calculator to find the amount of caffeine left in your system after 90 minutes. Now remember, when we look back at the table that we had, this table was in hours. So we would have to change this 90 minutes to hours. We all know that 90 minutes is 1.5 hours because it's 60 minutes in an hour. So 1.5 hours is 90 minutes. Okay, so now that we have that, we could just type in 1.5 and then we have 128.80 or 0.79. Okay, now to do this on the graph, so as you see here, this graph, I would have to do y equals the 180 parenthesis 0.80 to the X power. And then I will have to change my X values here. So let me go here. Wait a minute, let me make sure nothing else. Okay, that's good. All right, so I go to this tool here. My X values are a little too large. So what I'll do, I'll just go 0 till about, let's see, 300. Okay, by doing 0 to 300, if you notice here, we're showing a graph here. So they want us to go where x is basically 1.5. So we could click on this graph and just drag it. And as you see, it's a little hard to get to the 1.5 because it's skipping a little bit. That's a little hard. But like I said, you can type this in on the table. And as you see, it gave us the correct answer. All right. Now, and we could say here, there would be 128.8 milligrams of caffeine left in your system. Okay, number 9. It says use the graph to estimate the amount of time needed for the amount of caffeine to drop to 40 milligrams. Okay, so we'll click here. And we need to go down to where it's about 40 milligrams. Now, if you notice, when we get to 6, it's 6 hours, it gets to 47. So I'm trying to see if I can, okay, it still skips over. So what we could do is this. We know 7, between 6 and 7 is too high here. So we could just type in some values. Like let's just do 6.25, 6.5, 6.6, 6.7, 6.8. Okay, 6.8 take us down. So it'd be about what, 6.75, 74? Yeah, about 6.74. So we could say about 6.74 hours will yield 40 milligrams of caffeine left in your system. All right. So we go here to the back. The problem 10, it says use either table or trace commands or your calculator to try and come up with a more accurate estimate for the time needed. So basically, number 9 takes care of problem number 10 because we used the table, gave us a more accurate depiction here. All right, so let's go down here to number 11. It says make up a situation that could be modeled by each of the following exponential graphs. As always, extra points for creativity. Okay, here if you notice, this is exponential growth. So we could put that as the use of smartphones from the beginning. And then here, exponential decay, the use of landlines after cell phones. Okay, now that basically took care of section 2.5. We're going to go over here to section 2.6. 2.6 is very, very short. So that is why I'm going to go ahead and have us do 2.6. And as a matter of fact, we're going to be on page 188 for 2.6. But before I do page 188, I want to at least read the lesson title for 2.6 and also the objective. Okay, 2.6 title is on page 179. It says, follow the bouncing golf ball, learning objective, gather and organize data from an experiment, find an exponential curve of best fit for a real data set, and to study the rate of decay for an exponential equation. Okay, so on page 188, now the reason why we're not doing the full 2.6 is because we're not meeting face to face. We're meeting online. So we're not able to do the experiment like we would if we would have been face to face. But we can do some of the problems here on the next two pages on 188 and 189 for section 2.6. Okay, now it says the equation y equals 81.15 times 1.013 to the x can be used to model the population of the United States and millions of people based on a number of years since 1900. Identify the variables and the parameters in this equation and describe what the significance of each is in terms of population. So the variables. Y is equal to the population of US in millions. And then X is the number of years since 1900. All right, now the parameters. The 81.15 tells us the population in 1900. And, well, it tells us the population in 1900 was 81.15 million. And 1.013 tells us the population grows by 1.3% since 1900. I should put grows by 1.3% each year since 1900, because I don't want you to think that it's a one-time growth of 1.3%. Okay, now for number 2, use the equation in question 1 to complete the table. Then use the table to draw a graph of the equation. Don't forget to label an approximate scale on each axis. Now this says years after 1980. That was a mistake. It was supposed to be after 1900. So it's supposed to be after 1900. And it says population in millions. We got 81.15. We already have that from what was given to us. So now what I want to do, I am going to type in this equation that we had, which is y is equal to 81.15 parentheses 1.013 all taken to the x power. And then we're going to do a quick table. Okay, we have our table. And then we could just start typing in some of the values. We have 20. 20 would give us 105. We're rounding to decimal places. 0.07. We can go to 40. So it'd be 136.04. We can keep that 0. We can go to 60. So 176.14. Then 80. 228.06. And then 100. So it'd be 295.28. Okay, these are the values. Now they want us to graph it. If we look here, it'd be best if we did the bottom here by fives. So this would be 0, this would be 5, 10, 15, 20. This would be 40, 60, 80, 100, and then 120. And then going up the line here, it looks as though we'll be going by fives again, 5, 10, 15, 20. No, actually, we'll be going by tens, 10, 20, 30, 40. Let's do 50, 100, 150, 200, 250, 300, 350. And now we will graph this 0, 81. So this right here, we're going by 10. So it'll be somewhat like about here. Then we had 20, 105, about here. 40, we have 136, about here. And then 60, we have 176. 80, we have 228. And then 100, we had 295. It's real close to 300. And we can connect these. All right. So now number 3 says the equation y equals 81.15 illustrates exponential growth. The population was growing by, it'll be 1.3% each year. The model used in questions 1 through 3 was obtained using official data for every census from 1900 to 2010. The census is conducted every 10 years. Use your model to predict the population in 2015. Then find the population of the United States in 2015 online and compare it to your result. How accurate is it? So we have y is equal to 81.15 times 1.013 to the 115th power, because it's 115 years since 1900. And that will give us 358.41 million. And if we want to do that, we could just type in 115 here in the table, and that's what it will give us if we round to 2 decimal places. Now online, and you can look this up, online it was 325.13 million. Now it says how accurate is it? Our prediction is, what's that, about a little over 30 million. It's 30 million over the actual population. And we know that could be accounted for from, people moving out of the United States, people dying from various diseases, and so on. Okay, now we come to the last page of this exercise. It says, what do you think the result of your answers to question 4 say about population growth in the 21st century? It has slowed down slightly. Slowed down slightly. Still growing, but slowed down a little bit. It says, what if we use only more recent data? Since the census is conducted every 10 years, we'll have to use a different source. I use estimates from a site called Worldometers, which are based on multiple data sources that are likely to make them more accurate than the census. In fact, the census is historically not the best measure of the true population for a wide variety of reasons. The table below has data for years from 1900 to 2010. Use the data to find the exponential equation of best fit. Include 5 digits in all parameters. Okay, listen. So basically here they gave us new values that we have to do a new equation by. So we would add a table in Desmos and we would type in these values. We would have 0, look like it's done every 5 years. Okay, we'll go from 0 to 20, and now we'll type in their values: 254.51, 268.04, 284.59, 298.16, 312.25. All right, so now we have this. Now we have to find our equation. What we would do, we will go here and we have y. Now we know it's y equals ax plus b. I mean a times b to the x. So we have y, the tilde, ab. Well, we have to do y1 because our table has y1. So y1 ab to the x1 power, because our table has the x1 value. Now, whenever you do an exponential regression formula, you must click the log mode. You have to click that, and then it will give you your answers. So now we have our equation, which would be y is equal to, and we're going to round to 2 decimal places, 255.06 times 1.01 to the x power. That will be our equation. Okay, now it says here, it says here includes 5 digits in all parameters. So this was 5 digits. This is not 5 digits. So I have to add, we got 1, 2, 3. I have to add 2 more digits. So it'll be 04. Let me see. 0104. Okay. So it'd be y equals 255.06 times 1.0104. So we have to have 5 digits. Okay, so this is our equation. I'm going to rewrite it because it is kind of bunched up there. So this is our equation. Now we come here to number 7. It says, based just on the base of the exponential in your equation, do you think this equation is likely to give a better estimate for the 2015 population than our first model? Why or why not? I would say it would, because it has a slower growth rate than our original value. Okay, number 8. Use your equation to estimate the population in 2015 and 2050. Compare the 2015 estimate to the population you already found on the internet. Then search for a site that does population projections and see how your prediction compares. We don't have to do that. We're just going to do the actual just for the 2015. So we have y is equal to 255.06 times 1.0104 to the, now we'll go to 2015. So this is since 1990. So it'll be to the 25th power. So if we put that in our calculator, I mean, I guess I could have did the table, but we could just put this in our calculator. 0.06 to the 1.01 0.04. Then we would take all of that to the 25th power. And this would give us 303. Oh, I'm sorry, it's 330.35. So this gives us 330.35 million. So what we can write in comparison to the actual population, that this 330.35 million is much closer to the actual population of 300. What was that actual population we had earlier? 325.13 million. So it was actually more accurate. It was only a little less than 5 million off as opposed to, what was it, 30 million off. So it was much more accurate. So that is basically it. And as you all know, today you're supposed to do the 2-4 check assignment. 2-5 check assignment will be due tomorrow. And there is no 2-6 check assignment. So we are done.